Well, dear students, in the last lecture we have developed the idea about the formation of sigma and pi bonds, and I have given you one homework. So few of you have submitted the homework, not all of you. So try to do the problems and whatever homework and is given. So try to solve those questions because this, through question your concept becomes, more, revised. So see, I'm giving you one more opportunity to do this. All of you do this problem. I'm writing the answer. What should be the bond or sigma bond or pi bond or type of bond is formed. So, and all of you should, right, try to, draw the diagram because in case of orbital overlapping, because the next topic what I am going to start that involves this, orientation and overlapping of different orbitals. Means overlapping is the central part of covalent bond formation. So if you do not know the orientation of orbitals, then by overlapping you cannot make the covalent bond. So in first case, the answer of the first case is, in the first case you will get d pi bonding, d pi covalent bond, covalent bond. In the second case, YZ and PX, this is zero overlap, so no bond formation, no bond formation. This is a symmetry forbidden overlapping. In the third case, YZ and Y, so D pi P pi bonding, P pi covalent bond, and fourth one DYZ and PZ and Z axis is the molecular axis, so there is no bond formation. So all of you try to draw the orientation to justify this result. I am here written the result of this overlapping, right? Okay, so let's continue the formation of some more molecule. Like we can see that I have explained you the formation of F2 molecule, H2 molecule, N2 molecule, O2 molecule, right? The formation of these molecules, formation is explained by VBT model. VBT orbital overlap model. Atomic orbital overlap model. Overlap model. Right. See, I am not telling here that every property of all these molecules is explained by VBT model or this model what we have learned here. Formation, okay, formation is explained, but not every property. Like, whatsoever oxygen is present around us, this is very important point. Oxygen, what is present in our atmosphere, this is paramagnetic in nature. This is paramagnetic. Paramagnetic in nature. Right? This is paramagnetic in nature. Paramagnetic means have unpaired electron. Unpaired electron or electrons. Right? Means the oxygen which is present around us, that is paramagnetic in nature. So this very important property of this molecule is not explained on the basis of this VBT. Or what we have, I have shown you the formation of O2 molecule here somewhere. See here. In this molecule, there is no unpaired electron. See here, this electron is paired, this electron is paired, in sigma electron is paired, pi electron is paired, and here these are all are paired. So if you consider this model of bonding, what we have already gone through, this theory cannot explain the property of oxygen molecule, paramagnetic nature, because in every point here it is stated that okay, orbitals will overlap and electron becomes paired. So this theory, what we have here, valence bond theory, overlapping of orbital, this cannot explain fully all the properties of molecule. So if it cannot explain the property of O2 molecule, then see nitrogen molecule, this is diamagnetic, means there has no unpaired electrons in nitrogen molecule. Okay, by this theory you will get, okay, in nitrogen there is no unpaired electron, but how we can confirm that okay this is true or false? Because here in this case there is no unpaired electron in this bonding, but the molecule is paramagnetic. Molecule is paramagnetic, and here nitrogen there is no unpaired electron and it is diamagnetic. So we cannot link these two things together by this model. So definitely we need some other theory. Although what I am going to discuss here, next theory, that is also not able to explain the formation of O2 molecule. So ultimately when I will discuss molecular orbital theory, then that theory only can explain this behavior of oxygen molecule. So the magnetic behavior of molecules is also a very important property of matter, and it is not explained by this valence bond theory or hybridization. Then ultimately we are using molecular orbital theory for simple molecules which able to explain this, right? But see here, I have written something different. I have not written here all the properties of molecule. I have written here formation. So formation is explained by VBT, but not all the properties, right? So I think it is clear to all of you that VBT can explain the formation of these molecules, right? Now see, we have certain molecules and not certain molecules, many molecules, even formation of which cannot explain by this VBT. Although the formation of these small molecules is explained by VBT, so this was the beginning of VBT. Now VBT, when applied on the molecules like water, methane, ammonia, it cannot explain the formation of all these molecules. Even in the formation, properties far apart, right? So let's do the formation of methane molecule and try to apply this VBT on methane molecule, right? So see, this is CH4. So I am treating this molecule as per the valence bond theory. So what is the central atom here? Carbon. So what is the electronic configuration? 1s2, 2s2, 2px1, 2py1. This is the ground state electronic configuration. And as per this VBT, only two unpaired electrons this carbon atom have, so it will form two covalent bonds, because orbitals having paired electron, they do not participate in the bonding. So with the help of VBT, you cannot explain the formation of four covalent bonds in carbon, basically, right? Because in this state, in ground state, carbon is bivalent. Carbon is bivalent. Only two unpaired electrons are there. Only two unpaired electrons are present. So carbon is not a bivalent species, because no stable species known in which carbon is bivalent. Okay, some species are known in which carbon is bivalent, like if you see this carbene, or methylene. But it is what? Unstable. Right? Carbon forms stable molecules. Forms stable molecule in covalency 4, right? So how to justify this 4 covalency? So if you excite this 2s electron in 2pz, so 1s2, 2s1, 2px1, 2py1, 2pz1. Now carbon has 4 unpaired electrons. Carbon has 4 unpaired electrons. Now this can form 4 covalent bonds with 4 other hydrogen atoms. Now see, apply the valence bond theory. So how to represent first this see, 2s is spherical, and now 2px, see, this is 2px, this is 2py, and this is 2pz. 2pz, right? So if you consider here, one electron in S, one electron in Px. Suppose that one electron is here, one electron is here, and one electron is here, and one electron is here, and this 2s electron, suppose that I am putting here, right? Now see, hydrogen has one s1, so one hydrogen which is on this because nuclei should be here of hydrogen, and this is the carbon nuclei, this is the carbon nuclei. Now 2s and 1s they overlap, 2s and 1s, so this is 1s and 2s overlapping. Now if you show the other hydrogen atoms, here overlapping, here overlapping, right? Right? So this is the formation of molecule of this. Now tell me, okay, this is non-directional, 2s orbital is non-directional, 1s is non-directional, so there is no, I mean, point of bond angle between these two. But you know, px, py, pz are perpendicular to each other. So in carbon atom, the three hydrogen atoms in methane molecule, in the three hydrogen atoms, they should be, I mean, what should be the bond angle between them? As the bond angle between px, py and pz, what is the bond angle between px, py and pz? 90 degree, 90, 90, 90 degree. So the HCH bond angle, HCH bond angle, this should be equal to 90 degree. 3 HCH bond angle and 1 HCH bond angle, I mean, that could be anything, right? That could be anything because this is 2s overlapping. So don't consider that orientation of that. Only if you talk about these three. So this type of structure should be there for methane. But what experimentally we have observed the structure of methane, the experimental value of carbon hydrogen, I mean bond in methane, bond angle and bond length also, because you know here 2s, 2s, 1s, 1s, 2s overlapping, this have the bond length shorter than 2s, sorry, 1s and 2p overlapping, 1s, 2p, three bonds are there, so this is the order of bond length. Bond length as per this model, as per this model. So this methane molecule, this have bond angle, HCH bond angle is 104.5 degree, determined by X-ray, X-ray diffraction methods. So all four CH bond angle. See, this is a regular tetrahedra, and how to make the regular tetrahedra? If you want, you can prepare this regular tetrahedra by considering a cube. Consider a cube take the center of cube. Center of cube is the, put carbon at the center of the cube and put 4 hydrogen at the alternate corners of the cube. You will get the perfect tetrahedra with this bond angle 104.5 degree, right? So this feature of this molecule, even overlapping and bonding, this is not at all explained by this VBT, right? Not explained by VBT. Similarly, if you consider water molecule or ammonia molecule first, if you take ammonia molecule and consider nitrogen 1s2, 2s2, 2px1, 2py1, 2pz1. So, I can write here some more information that all 4 bond, which bond? CH bond are CH bond have same energy and length, right? In methane, and all four HCH bond angles are equal. But as per VBT, 3 bonds should be at 90 degree and 1 is non-directional, right? Now see in case of nitrogen, so if you see, this is these 3 will form the covalent bond because they have unpaired electrons, so they will form the bond. So 1 electron and hydrogen 1s1, so hydrogen will overlap, and electrons are paired like this. So N, H, H. So what should be the bond angle here? What should be the bond angle? HNH bond angle, HNH bond angle, this should be 90 degree as per the this model of overlapping. And X-ray suggested the bond angle H and H bond angle 107.5 degree. Now tell me which value you are going to consider correct, this or this. Obviously this is correct. So even ammonia molecule, formation of ammonia molecule is also not explained by this VBT model. Similarly, if you take water molecule, so oxygen 1s2, 2s2, 2px, 2, 2py1 and 2pz1. So in this case, 2py and 2pz. Right, hydrogen, 2 hydrogen. So which overlapping? 1s and 2py overlapping and 1s 2pz overlapping, right? So what should be the bond angle here? As per this theory, this bond angle should be 90 degree, right? What X-ray suggested for this? The X-ray suggested the bond angle for this water molecule is 104.5 X-ray, right? So experimentally you are getting 104.5, but what I mean VBT model has suggested that okay, means VBT means overlapping of atomic orbitals, pure atomic orbitals, suggested that it should be 90 degree. Okay, so see, I have taken these three basic or smaller molecules. So this theory cannot explain the formation of these molecules. So we can put a note here that the simple overlapping, now see the simple overlapping of pure atomic orbitals cannot explain the formation of molecules, right? Cannot explain the formation. Properties, the secondary issue, right? Properties will come next, but formation, even formation is not explained by this I mean model. Formation of molecules, right? Like CH4, H2O, ammonia, and you can apprehend so many number, etc. Then we need another theory. So Linus Pauling suggested instead of overlapping of pure orbital, Linus Pauling suggested the overlapping of hybrid orbitals, hybrid with hybrid or hybrid with pure. So he suggested the mixing of atomic orbitals and proposed a hypothetical concept known as hybridization. So hybridization is nothing but it is the mathematical manipulation of atomic orbitals which suggests the mixing of atomic orbitals. Why? To explain the fact. The fact is that this bond angle is 104.5. The fact is that all bond lengths and bond angles in methane are equal. The fact is that this ammonia molecule has bond angle 107.5. So to define these facts, Pauling suggested this hypothetical concept, and this is known as hybridization. Hybridization, right? So, see what is this hybridization? So, hybridization you can simply define the mathematical manipulation of atomic orbitals. This is the mathematical manipulation of pure atomic orbitals. Mathematical manipulation of pure atomic orbitals, right? So what are the key features of this hybridization? In this hybridization, it is suggested that atomic orbitals of a central atom or an atom, not necessarily that every time you consider central atom, all other atoms may also have hybridization. So we can, in general statement, we can say the atomic orbitals of an atom, right, in a molecule, they mix together as per the requirement of explaining the geometry. So they mix together and produces some hybrid, because you know the name itself, hybrid, means they produces an orbital with mixed character. So see what is the requirement for this hybridization, which type of orbital may go into the mixing. So I am writing here point wise. See, for hybridization, the energy of mixing orbitals should be comparable. First requirement, the energy of atomic orbitals should be comparable. First point. Second point, for mixing of atomic orbitals, it is not necessary that orbital have one electron, or orbital has two electron, or orbital has no electron. As in the VBT, it is mandatory that orbitals, atomic orbitals which are going to overlap, they must have one electron. But here no restriction, means atomic orbital with one electron, with two electron, or without electron can mixed, can mix, right? So it is not any requirement that orbital must have an electron, right? So these two are the, primary requirement. You can say energy requirement is must. If there is a huge difference in the energy, then there is no mixing. And what you can define mixing as mixing of S, if S is mixed with S, so can you consider this is hybridization? If S and S mix, so can you consider this hybridization? 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 The answer is no. Mixing should be of different character, means mixing of S and P, this could be considered as a hybridization. Mixing of S and D, this could be considered as a hybridization. Mixing of S, P and D, this could be considered as a hybridization. But mixing of S into S and mixing of P into P and P mixing, this is not hybridization, right? So mixing of two or more different character orbital, right? This is also you can consider as a requirement. Okay, so this is the background of this hybridization. Now see, I have developed my own way of explaining this hybridization. So see, each and every s orbital has some identity. Like s orbital is non-directional and it is spherical in nature. Only principal quantum number is required to define this. It has some size also, distance from the nucleus, what distance you are taking up to the maximum distance, that is the surface boundary condition. Similarly, P have also some identity, like it has some energy, it has some orientation, it has some length. Similarly, every atomic orbital has some identity, right? Every. So, atomic orbitals have certain properties like size, like energy, like shape, like some orientation. So atomic orbitals have such properties, and electrons as well. Electron or electrons or without electron. right? So these are the certain properties of atomic orbitals. So I have developed a concept, and in that concept, I am explaining this hybridization on the basis of the conservation and non-conservation of the properties of atomic orbitals. And one more property I can add here. Uh, the number of atomic orbitals, right? So these are the certain feature of atomic orbitals. So after mixing and before mixing every atomic orbital is pure, it has certain properties. After mixing, some of the properties from here I have properties which I have listed here. Some of the properties are conserved and some of the properties are not conserved. So before and after mixing, the atomic orbitals may retain its some of the properties and may not retain some of the properties. So before and after mixing, some of the above properties of atomic orbitals are conserved and some of them are not conserved. Not conserved. Right? Now see. Conserved, not conserved. Not conserved. See, and here this property. Right? First property, number of orbitals. Number of orbitals. So, number of orbitals, they are conserved. Right? Number of orbitals are conserved. Means, if n atomic orbitals are mixed together, so you always get an hybrid orbital. Hybrid orbital. Means in hybridization, there is no loss or gain of orbitals. Okay? If there is a hybridization, means there is no loss or gain of any atomic orbitals. So this is the first property. Now second, number of paired and unpaired electrons. Paired and unpaired electrons. Unpaired electrons. In a single word, you can say multiplicity. Multiplicity. So this is also conjunct. Means if your system, if your atom has some number of unpaired electrons before mixing, so after mixing, the same number of unpaired electrons should be there in the hybrid orbitals. You cannot change the multiplicity of the system before and after hybridization. Whatever you want, if your system is not, if your system is not, energetically favored for the mixing, or it is not appropriate for the mixing, then excitation and de-excitation should be done before mixing. Before mixing, whatever the state of your atom is, that is remains in the after mixing. So this is very, very important and essential point, right? Now see, next property, number of atomic orbitals and electrons. Now see, energy not conserved. Energy not conserved means the energy of hybrid orbital and the energy of this atomic orbital, if you compare, right? So the energy of hybrid orbital is not equal to the energy of what? Atomic orbitals. Total energy is conserved. Total energy, I am not talking about the total energy. I am talking about the energy of hybrid orbital and energy of atomic orbital. Right? So if you compare the energy of atomic orbital and energy of hybrid orbital, both are different, means not conserved. Total energy of the system is conserved. Means system means whole, molecule. That is, there is no change. So energy of atomic orbital, so we can write here energy of atomic orbital. Energy of atomic orbital is not equal to the energy of hybrid orbital. Hybrid orbital H, right? Now come to the next point. Shape, size, shape and size, they are also not conserved. Means if S and P are mixing together, then you will get some different shape and size orbital, hybrid orbital. Means shape and size of atomic orbital is not retained in the what? Hybrid orbital. Okay, that will change. And most important point is the orientation. The most important property is the orientation. Orientation, that is also not conserved. Means orientation of atomic orbital is not equal to the hybrid orbital. Means for example, S orbital is non-directional and P orbital is directional. P orbital Px, Py, Pz, or at 90 degree from each other. This is the orientation of p atomic orbitals. So when they mix, they will get some other orientation, not 90 degree. So the orientation of atomic orbital, orientation of atomic orbital is not equal to the orientation of hybrid orbital, right? So in this way, try to understand what is the theory of hybridization, right? So in hybridization, see, some of the properties of these atomic orbitals are remain same and some of the properties are changed, right?